Right now, NASA has the technology to send humans to Jupiter. The rockets exist. The navigation systems work. The life support could theoretically sustain a crew for the journey. Scientists have mapped every gravitational assist, calculated every trajectory, and solved nearly every problem involved in reaching the largest planet in our solar system. There is just one detail nobody talks about publicly. The mission architecture collapses the moment you try to come home. Getting to Jupiter was never the real challenge. Every spacecraft we have ever sent there was designed to die. The fuel required for a return trip creates a mass problem that spirals beyond engineering solutions. The radiation exposure accumulates past survivable limits, and the systems that kept you alive on the way out will have degraded past reliability by the time you need them most. If you enjoy exploring the huge challenges humanity faces exploring space and our solar system, hit that like button and subscribe. Now, settle in and make yourself comfortable. Let's begin. Jupiter floats in the outer solar system like a cosmic lighthouse, visible to the naked eye on clear nights, seemingly close enough to visit. Ancient Romans named it after the king of their gods. Galileo pointed his primitive telescope at it 4 centuries ago and discovered moons orbiting another world for the first time in human history. Every civilization that looked upward noticed this wandering star, brighter than anything except Venus, moving slowly against the fixed background of distant suns. And in a strange way, Jupiter is close enough to visit. Humanity has already sent 9 spacecraft to Jupiter. Pioneers 10 and 11 blazed the trail in the 1970s, becoming the first human-made objects to cross the asteroid belt and encounter the giant planet. Voyagers 1 and 2 followed with their golden records carrying human greetings into the void. Galileo orbited Jupiter for 8 years, dropping a probe into the swirling atmosphere and transforming our understanding of the Jovian system. Juno circles it right now, sending back images of polar cyclones and auroras that dwarf anything on Earth. Every single one of these missions succeeded in reaching Jupiter. The navigation works. The propulsion works. The communication systems maintain contact across hundreds of millions of miles. If you only wanted to touch Jupiter's domain, the engineering problems are largely solved. This creates a dangerous illusion. When space agencies announce ambitions to send humans deeper into the solar system, Jupiter seems like a natural destination. Mars gets the headlines, but Jupiter offers something Mars cannot. Its moons contain more water than all of Earth's oceans combined. Europa hides a liquid ocean beneath miles of ice, where conditions might support life. Ganymede is larger than the planet Mercury, and possesses its own magnetic field, the only moon in the solar system with this feature. Callisto offers a stable platform far enough from Jupiter's radiation belts to serve as a potential base. Io displays the most violent volcanic activity in the solar system, with plumes shooting hundreds of kilometers into space. The Jovian system is not a single destination, but an entire miniature solar system waiting for exploration. The public imagines astronauts floating past the Great Red Spot, planting flags on Europa, returning home as heroes who ventured farther than any humans in history. Science fiction has prepared us for this narrative. We have watched fictional crews travel to Jupiter in films and novels. Arthur C. Clarke sent astronauts there in his famous series. Stanley Kubrick visualized the journey in cinema that shaped how generations imagined deep space travel. The journey appears dramatic, but achievable. The destination appears hostile, but survivable. The return appears challenging, but inevitable. Nobody explains why this will never happen. The fundamental problem hides in a single word that appears nowhere in the glossy mission proposals, nowhere in the inspiring artwork of astronauts gazing at Jupiter's storms, nowhere in the optimistic timelines that space enthusiasts share on social media. Return. Every spacecraft humanity has sent to Jupiter was designed from the first blueprint to die there. Galileo did not carry fuel for a trip home. It carried precisely enough propellant to enter Jupiter orbit and conduct its science mission before controllers deliberately crashed it into the planet's atmosphere to avoid contaminating Europa with Earth microbes. Juno will meet the same fate when its mission concludes. The Voyagers are still travelling, but outward, forever outward, with no possibility of return built into their design. Pioneer 10 and 11 drift through interstellar space. Their missions complete, their trajectories carrying them away from the Sun until the heat death of the universe. This was not an oversight. This was physics. The moment you try to design a mission that brings humans back from Jupiter, the entire architecture collapses. Not gradually. Not with engineering challenges that clever solutions might address. The collapse is mathematical and absolute. The energy required to return from Jupiter creates mass requirements that grow faster than any rocket can lift. The mission duration exposes crews to radiation doses that accumulate toward lethal thresholds. The systems that kept astronauts alive during the outbound journey will have degraded past reliability by the time they need to function for the return. Getting there was never the real challenge. Let me show you exactly why. Jupiter orbits the Sun at an average distance of 484 million miles. Earth sits approximately 93 million miles from the Sun. The gap between these orbits varies as both planets complete their years at different rates. Jupiter takes nearly 12 Earth years to complete one orbit, moving slowly through the zodiac while Earth races around the Sun 12 times. At the closest approach, called opposition, Jupiter lies about 365 million miles away. At the farthest separation, when the Sun sits between the two planets, the distance stretches past 600 million miles. To put these distances in perspective, consider that the Moon orbits Earth at an average distance of roughly 240,000 miles. The Apollo astronauts crossed this gulf in 3 days. Jupiter, at its closest approach, lies more than 1,500 times farther away than the Moon. At maximum separation, Jupiter is more than 2,500 times farther. If Apollo-era technology could reach the Moon in 3 days, reaching Jupiter would require years of continuous travel. These numbers sound abstract until you translate them into travel time and communication delays. Light itself, the fastest thing in the universe, requires between 33 and 52 minutes to cross this gulf depending on orbital positions. Radio signals carrying commands from Earth to a Jupiter-bound spacecraft experience this same delay. If something goes wrong at Jupiter, if an engine fails or a life support system malfunctions or a medical emergency strikes, mission controllers will not know about it for half an hour minimum. Their response will take another half hour to arrive. The crew handles every emergency alone for at least an hour before any guidance from Earth can reach them. For comparison, astronauts on the International Space Station can reach mission control in Houston within seconds. Ground controllers can walk crews through emergency procedures step by step, observing results and adjusting instructions instantly. Lunar missions experienced communication delays of only 1.5 seconds, barely noticeable in normal conversation. Mars missions face delays of 4 to 24 minutes, depending on orbital positions, long enough to make real-time conversation impossible, but short enough that ground support can assist with problems that develop over hours or days. Jupiter delays exceed anything humans have experienced during crewed spaceflight by factors that fundamentally change mission operations. A crew facing a life support emergency cannot call Earth for help and receive useful guidance. By the time mission control learns of the problem, the crew has already spent an hour dealing with it alone. By the time advice arrives, 2 hours have passed. The crew either solves problems independently or dies waiting for instructions that arrive too late to matter. History offers one partial parallel to such isolation. Antarctic explorers of the early 20th century pushed supply lines beyond any previous human experience. Shackleton and Scott led expeditions where rescue was impossible and self-sufficiency meant survival. Men died when conditions exceeded their preparations. Yet even those desperate ventures allowed for hunting seals, melting ice for water, and the theoretical possibility that search parties might eventually arrive. Jupiter permits none of these margins. No living off the land, no local resources to exploit, no search party that could reach a stranded crew within their lifetimes. Antarctica was the edge of survivability. Jupiter lies far beyond that edge, but communication delays represent the smallest problem. Spacecraft do not travel in straight lines between planets. They follow curved paths called transfer orbits that use the Sun's gravity to swing from one planetary orbit to another. The most fuel-efficient trajectory to Jupiter, called a Hohmann transfer orbit, takes approximately 2 to 3 years depending on launch windows and mission design. The spacecraft leaves Earth, coasts along an elliptical path that touches both Earth's orbit and Jupiter's orbit, and arrives at the outer planet with minimal fuel expenditure. This trajectory works because it exploits orbital mechanics rather than fighting against them. The spacecraft does not power its engines continuously for years. It accelerates briefly to leave Earth orbit, then falls freely through space along a path shaped by the Sun's gravity. Only when approaching Jupiter does it fire engines again, this time to slow down enough for Jupiter's gravity to capture it into orbit. Some proposals use gravitational assists from Venus or Earth itself to reduce fuel requirements further. The Galileo spacecraft used 1 Venus flyby and 2 Earth flybys before reaching Jupiter. Cassini swung past Venus twice, Earth once, and Jupiter once before arriving at Saturn. These planetary billiard shots save enormous amounts of fuel but add months or years to the journey time. Each flyby requires precise timing. The spacecraft must arrive at each planet exactly when that planet's position allows the desired trajectory change. Miss the window and the entire sequence fails. NASA's crude mission concepts for Jupiter typically assume flight times between 2 and 6 years each direction, depending on propulsion technology and trajectory choices. Add time for orbital operations around Jupiter or its moons, perhaps 6 months to a year of scientific activities, and total mission durations stretch toward a decade or beyond. 10 years. The same span that separates a child from a teenager, a newlywed from a parent, a career from retirement. Astronauts who departed in their 30s would return in their 40s. Those who left children behind would return to find young adults who spent their formative years with an absent parent. Spouses would age a decade apart. The world they remembered would have changed in ways they could not predict during years of isolation, hundreds of millions of miles from home. Political leaders would change. Technologies would advance. Cultural references would shift. The astronauts would return as strangers to a world that continued without them. Now comes the critical asymmetry that makes return impossible. When mission planners design an outbound journey to Jupiter, they calculate fuel requirements based on changing the spacecraft's velocity enough to accomplish 3 main tasks. First, escape Earth's gravity well and enter a heliocentric orbit around the Sun. Second, follow a transfer trajectory that intersects Jupiter's orbit at the right time and place. Third, slow down enough upon arrival to be captured by Jupiter's gravitational field rather than flying past into the outer solar system. These velocity changes, measured in kilometers per second and called delta V in aerospace engineering, determine how much propellant the mission requires. The outbound trip to Jupiter requires approximately 9 to 14 kilometers per second of total velocity change, depending on the specific trajectory, mission timeline, and operational requirements. This is enormous by spaceflight standards. For comparison, reaching low Earth orbit from the surface requires about 9 kilometers per second. This single velocity change represents the culmination of decades of rocket development and still requires massive vehicles that discard most of their mass during ascent. A trip to Mars needs roughly 4 kilometers per second beyond Earth orbit. Jupiter demands velocity changes that exceed anything humans have accomplished with crude vehicles by substantial margins. But here is where the mathematics turn murderous. The return trip requires the same velocity changes in reverse. To leave Jupiter's gravitational influence, the spacecraft must accelerate to escape velocity from whatever orbit it occupies. Jupiter's gravity well is deep, far deeper than Earth's. The planet contains more mass than all other planets in the solar system combined. Escape velocity from Jupiter orbit depends on altitude, to more than 20 kilometers per second for low orbits. Then the spacecraft must travel back along a transfer orbit to Earth's vicinity, another journey of 2 to 3 years. Finally, it must slow down enough to be captured by Earth's gravity, rather than flying past into the void. A round trip to Jupiter requires roughly double the velocity change of a one-way mission. This does not mean double the fuel. The rocket equation describes an exponential relationship between velocity change and fuel mass. Every additional unit of velocity requires fuel. That fuel has mass. That mass must be accelerated along with the spacecraft, which requires more fuel, which has more mass. The requirements compound recursively until the spacecraft becomes almost entirely propellant. Part 2 will examine this tyranny in detail, but the implication is immediate. Fuel requirements do not double for a round trip. They increase by factors of hundreds or thousands. This brings us back to the return problem. Getting to Jupiter is a solved problem because we do not try to come back. Every successful Jupiter mission dumped the return fuel requirements entirely. They launched lighter spacecraft that carried only outbound propellant. They maximized scientific instruments instead of return capabilities. They accepted that the mission ended at Jupiter rather than continuing home. Human missions cannot operate this way. Astronauts are not expendable instruments to be discarded after data collection. The moral imperative to bring crews home transforms the mass equation from difficult to impossible. Every kilogram of food, water, and oxygen for the return journey must be launched from Earth along with the fuel to transport it. Every backup system needed for the return trip adds weight that demands more fuel. Every radiation shield protecting the crew during the long journey home increases the mass that the propulsion system must accelerate. The spacecraft grows heavier. The fuel requirements explode. The launch vehicle needed to lift this mass from Earth does not exist. The orbital assembly required to construct such a vehicle would consume resources beyond any space program's budget. And we have not yet even discussed what Jupiter itself does to the humans attempting this journey. Consider what success looks like for the outbound leg alone. A crew of 4 to 6 astronauts launches from Earth aboard a spacecraft designed for deep space travel. The vehicle includes habitation modules, large enough for years of living in confined spaces without privacy. Exercise equipment sophisticated enough to combat the bone and muscle loss that afflicts bodies in weightlessness. Medical facilities capable of handling emergencies that cannot wait for evacuation. Food storage and preparation systems for thousands of meals. Water recycling equipment that must function flawlessly for years. And communication systems that remain functional across hundreds of millions of miles despite years of exposure to radiation and temperature extremes. The habitation modules must provide not just survival but psychological sustainability. Crews confined for years in small spaces without the ability to step outside. Without fresh air, without new faces, without the simple pleasure of walking down a street or visiting a restaurant, face psychological challenges that no previous spaceflight has approached. They must somehow create an environment where humans can maintain mental health across timescales that typically produce serious psychological deterioration in isolated populations. The outbound journey takes approximately 3 years, using efficient trajectories. During this time, the crew monitors systems, conducts maintenance, performs scientific observations, exercises for hours daily, manages psychological stress, resolves interpersonal conflicts, and prepares for Jupiter operations. They watch Earth shrink from a blue marble to a pale dot to an invisible point among countless stars. They experience isolation beyond anything astronauts on the International Space Station ever faced. They spend 1,000 days in artificial environments surrounded by vacuum, knowing that the nearest help lies years away. By the time they reach Jupiter, they have traveled farther from home than any humans in history. They have experienced communication delays that make real-time conversation with Earth impossible. They have celebrated birthdays and missed family events and processed news of deaths and births on a planet that grows more abstract with each passing month. And they have not yet begun the dangerous part of the mission. Everything accomplished during the outbound journey must now be repeated in reverse under far worse conditions. The spacecraft systems have aged 3 years in the harshest environment humans have ever entered. Filters have collected contaminants. Seals have endured temperature cycling between baking sunlight and freezing shadow thousands of times. Electronic components have absorbed radiation damage. Mechanical parts have experienced vibration and stress from attitude adjustments, course corrections, and daily operations. The crew has also changed. Their bodies have adapted to weightlessness in ways that make returning to gravity dangerous. Their psychological reserves have been tested by years of confinement. Part 3 will examine these physiological and psychological tolls in detail. Now, they must trust their lives to equipment that has operated continuously for 3 years, in conditions that accelerate every failure mode engineers understand. They must bet that nothing critical will fail during the 3-year return journey. They must hope that the return propulsion system, which has sat dormant for years while exposed to cold, radiation, and vibration, will ignite when they need it most. Mission planners understand these risks. Their solution is redundancy. Build backup systems for every critical function. Carry spare parts for components likely to fail. Design around single points of failure so that no individual malfunction can doom the mission. But every backup system adds mass. Every spare part requires launch fuel. Every redundant component makes the spacecraft heavier, which requires more fuel, which adds more mass, which requires more fuel. The mission architects face an impossible choice between stripping away safety margins and watching mass requirements spiral beyond any launch capability. This is not a choice between acceptable risks. This is a choice between different flavors of certain death. Consider how different this situation appears for Mars missions. Mars lies much closer to Earth than Jupiter. At closest approach, approximately 34 million miles separate the two planets. At maximum distance, the gap reaches about 250 million miles. These distances are still enormous by terrestrial standards, but they are an order of magnitude smaller than Jupiter distances. A round trip to Mars requires total velocity changes of approximately 8 to 12 kilometers per second. This difference matters enormously for mission design. The fuel requirements for Mars, while massive, remain within the bounds of super-heavy launch vehicles that exist or are under development. The journey duration allows life support systems to function within their design limits. The radiation exposure, while significant, stays below immediately lethal thresholds for crews with appropriate shielding. Equipment degradation over 2 years is manageable in ways that degradation over 10 years is not. Mars is at the edge of human capability. NASA and other space agencies actively plan crewed Mars missions for the coming decades. The engineering challenges are severe, but not insurmountable. The risks are high, but potentially acceptable. Jupiter lies far beyond. At Mars distances, mission failures might be recoverable. Abort options exist. If systems fail early in the outbound journey, the crew might be able to return to Earth. If failures occur at Mars, the crew might survive long enough for the next return window. Communication delays of minutes allow some real-time problem-solving with Earth-based controllers. At Jupiter distances, every failure is final. No rescue mission can reach them in time. If life support fails at Jupiter, the crew cannot wait years for help to arrive. A crew that discovers a critical failure at Jupiter has no options except to watch their situation deteriorate over months until the inevitable conclusion. No communication with Earth can solve problems that unfold faster than radio signals can travel. Medical emergencies illustrate the evacuation problem with brutal clarity. On Earth, serious illness triggers a cascade of institutional response. Ambulances transport patients to hospitals within minutes. Emergency rooms stabilize critical conditions. Specialists perform surgeries that require sterile environments, sophisticated imaging equipment, and teams of trained professionals working in coordination. Blood transfusions replace lost volume. Transplant networks provide replacement organs. The entire apparatus of modern medicine stands ready to intervene when biology fails. At Jupiter, none of this exists. A crew member who develops appendicitis faces a ruptured appendix and peritonitis unless a fellow astronaut can perform an appendectomy using onboard surgical equipment. Appendicitis occurs in roughly 100 people per 100,000 per year. Over a 10-year mission with 6 crew members, the probability of at least one appendicitis case approaches 5%. Not high. Not negligible either. Can astronauts perform surgery in weightlessness? Blood does not pool in wounds under zero gravity. It forms floating spheres that drift through the cabin, contaminating equipment and obscuring the surgical field. Intestines do not stay retracted. They float outward, requiring restraint systems that do not exist in terrestrial operating rooms. Anesthesia delivery differs when drugs distribute through bodies adapted to weightlessness. Post-operative care occurs in an environment where wound healing proceeds differently than on Earth. Astronauts receive extensive medical training. They can handle many emergencies that would require professional intervention on Earth. They are pilots, engineers, and scientists who learned medical procedures as additional skills. The difference between an astronaut performing emergency surgery and a trained surgeon performing the same procedure represents the difference between desperate improvisation and practiced expertise. Cancer presents an even grimmer scenario. Radiation exposure at Jupiter virtually guarantees elevated cancer risk. Most radiation-induced cancers develop years after exposure, manifesting after the crew returns to Earth if they return at all. But some cancers develop faster. Leukemia can appear within 2 to 5 years of significant radiation exposure. A crew member who receives high doses during a radiation storm early in the mission might develop leukemia symptoms during the return journey. There is no chemotherapy protocol for deep space, no radiation oncology suite in the spacecraft design, no bone marrow transplant capability, hundreds of millions of miles from the nearest hospital. A crew member diagnosed with leukemia at Jupiter faces death without meaningful treatment options. The medical supplies aboard any realistic Jupiter mission cannot address every possible condition. Mass constraints force choices. Carry antibiotics for infections. Carry analgesics for pain. Carry splints for fractures. Carry suture kits for lacerations. But do not carry dialysis equipment for kidney failure. Do not carry bypass capability for cardiac emergencies. Do not carry surgical robots for conditions requiring precision beyond human hands. Every medical condition beyond the mission's preparation becomes a death sentence delivered in slow motion. And every year of mission duration increases the probability that some condition will emerge that the spacecraft cannot address. Bodies accumulate damage, random mutations occur, latent conditions manifest. The longer the mission continues, the more opportunities biology has to fail in ways that mission planners could not anticipate and medical supplies cannot treat. The mission only fails once you try to come home. The return journey demands everything the outbound trip required, plus years of additional system operation. The life support that kept the crew alive must continue functioning for another 3 years. The propulsion systems that brought them to Jupiter must work flawlessly for the return burns. The navigation and communication equipment must remain operational across another 3 years of degradation. But the return journey also demands propellant reserves that make the entire mass budget collapse. All that return fuel had to be carried from Earth, accelerated through every maneuver of the outbound trip, protected for years of storage at Jupiter, and kept ready for the moment when the crew needs to leave. This asymmetry defines the fundamental barrier to Jupiter exploration, not the going, the coming back. What makes this barrier particularly cruel is how invisible it remains until you work through the mathematics. Jupiter looks reachable. The distances are large but finite. The journey times are long but survivable. The engineering challenges are severe but not obviously insurmountable. Space enthusiasts discuss Jupiter missions with the same optimism they bring to Mars discussions, as if the difference were merely one of degree rather than one of kind. Only when you require a return ticket does the mission architecture reveal its fatal flaw. A spacecraft that could make the round trip to Jupiter using chemical propulsion would be larger than any structure humans have ever launched. It would require assembly in orbit from dozens or hundreds of separate launches. It would consume the entire annual output of multiple space agencies working together for years, and even then, it would offer margins so thin that minor system failures would cascade into mission loss. And we have not yet discussed what happens during the years this impossible spacecraft spends in Jupiter's neighborhood, where radiation from the largest planet in the solar system delivers doses that accumulate toward lethal thresholds, while the crew waits for their return window to open. We have not yet examined how the timing constraints of orbital mechanics create windows so narrow that delays become death sentences. We have not yet explored how system degradation compounds across decade-long missions until no amount of redundancy provides acceptable reliability. The return problem only grows worse from here. What comes next reveals the tyranny of the rocket equation in full, where every proposed solution to one problem creates new problems that demand additional solutions, each adding mass that the mission cannot afford, in a spiral that has no bottom and no escape. Imagine filling a car with fuel for a road trip. You calculate the distance, estimate your mileage, and pump enough gasoline to reach your destination with comfortable reserves. Simple arithmetic governs the relationship between fuel and distance. Drive twice as far, burn roughly twice the fuel. Drive 3 times as far, burn roughly 3 times the fuel. The relationship is linear, predictable, manageable. A cross-country trip requires perhaps 15 tanks of gas. Double the distance, and you need roughly 30 tanks. The math is straightforward. Spaceflight operates on different mathematics entirely. The rocket equation transforms fuel requirements from linear calculations into exponential nightmares. This single equation, derived by a Russian schoolteacher named Konstantin Tsiolkovsky in 1903, governs every mission humanity has ever launched and every mission we will ever attempt. Tsiolkovsky worked out the mathematics decades before the first rocket reached space. He understood the fundamental relationship between fuel, mass, and velocity that would constrain all future space travel. The equation does not negotiate. It does not bend to human ambition. It simply describes reality with mathematical precision that crushes dreams. When a spacecraft needs to change its velocity, it must expel propellant at high speed in the opposite direction. Newton's third law provides the thrust. For every action, there is an equal and opposite reaction. Push exhaust backward, and the rocket moves forward. The faster you expel the exhaust, the more efficiently you convert propellant mass into velocity change. This exhaust velocity, a measure of engine efficiency, determines how much velocity change each kilogram of fuel can provide. But here is where the mathematics turn cruel. The propellant has mass. That mass must be accelerated along with everything else the spacecraft carries. To carry fuel for later maneuvers, you need fuel to accelerate that fuel. To carry that extra fuel, you need still more fuel. To carry that additional fuel, you need even more fuel beyond that. The requirements compound recursively. The mass grows exponentially. The mathematics curve upward toward vertical asymptotes where no amount of fuel can accomplish the required velocity change. Tsiolkovsky expressed this relationship in an equation of deceptive simplicity. The velocity change a rocket can achieve equals the exhaust velocity of its engine, multiplied by the natural logarithm of the ratio between initial mass and final mass. Written on a napkin, it looks almost trivial. Applied to real missions, it reveals why interplanetary travel pushes the boundaries of physical possibility. The natural logarithm function grows slowly, very slowly. To double your velocity change, you must square your mass ratio. To triple your velocity change, you must cube your mass ratio. The fuel requirements do not increase proportionally with the velocity demand. They explode exponentially. This mathematical relationship is not a technology limitation that better engineering can overcome. It emerges from the fundamental physics of momentum conservation. No propulsion system, no matter how advanced, can escape this relationship. The equation governs all reaction-based propulsion, from chemical rockets to nuclear thermal engines to ion drives. This relationship defines everything about deep space mission design. For a one-way trip to Jupiter, the rocket equation remains manageable. Difficult, demanding, requiring careful optimization of every gram, but solvable within the capabilities of existing or near-term technology. Mission designers calculate the velocity changes required for Earth departure, trajectory corrections, and Jupiter arrival. They work backward through the equation and arrive at fuel masses that can be launched with sufficient effort and budget. The moment you add return propulsion, the equation explodes. Here is why. A spacecraft bound for Jupiter must carry its return fuel from the moment it leaves Earth. Every kilogram of propellant reserved for the journey home must be accelerated through every maneuver of the outbound trip. It must be hauled across hundreds of millions of miles through the cold vacuum of interplanetary space. It must be protected from thermal extremes that cycle between baking sunlight and freezing shadow. It must survive micrometeorite impacts that sandblast everything in the solar system. It must resist radiation damage that degrades chemical bonds over years of exposure. Every kilogram of return propellant requires additional fuel to transport it to Jupiter. That transport fuel has mass. That mass requires its own transport fuel. That additional fuel requires still more fuel. The cascade continues until the spacecraft becomes almost entirely propellant, with only a tiny fraction of its launch mass dedicated to crew, cargo, and systems. Let me put specific numbers to this abstraction. Aerospace engineers measure velocity requirements in terms of delta V, the total change in velocity a mission requires. For a crewed round trip to Jupiter, using high-performance chemical rockets, mission studies estimate total delta V requirements of approximately 25 to 35 kilometers per second, depending on trajectory choices, operational requirements, and safety margins. This number requires context to appreciate its magnitude. Reaching low Earth orbit from the surface of our planet requires approximately 9 kilometers per second of delta V. This is the velocity change needed to accelerate from standing on the launch pad to orbiting at 17,500 miles per hour. Every rocket launch you have ever witnessed accomplished roughly this velocity change. The massive Saturn V, the graceful Space Shuttle, the sleek Falcon 9, all achieve approximately the same velocity change, enough to reach orbit. A trip to the Moon and back requires approximately 16 kilometers per second total. The Saturn V rocket, the most powerful launch vehicle ever successfully flown, could deliver approximately 130 tons to low Earth orbit. Even this immense capability barely sufficed for lunar missions with a 3-person crew and minimal equipment. The Apollo program required the largest rockets ever built, and those rockets could only send small capsules to the nearby Moon. A round trip to Mars requires approximately 8 to 12 kilometers per second beyond low Earth orbit, depending on the specific trajectory and mission design. This represents the edge of current technological capability. No nation has yet accomplished a crewed Mars mission, though multiple agencies plan to attempt it within the coming decades. The engineering challenges for Mars are severe but appear solvable. The mass requirements, while enormous, fall within conceivable mission architectures. A round trip to Jupiter requires roughly double the delta V of a Mars mission, 25 to 35 kilometers per second. This accounts for Earth departure at higher velocity to reach Jupiter's distant orbit. Jupiter orbit insertion requiring substantial braking against the giant planet's gravity, Jupiter departure at escape velocity, and Earth arrival requiring deceleration to avoid flying past into the void. Now, apply the rocket equation. Using liquid hydrogen and liquid oxygen propulsion, the highest performing chemical rocket combination that exists, a spacecraft attempting this mission would need to launch with a mass ratio exceeding 1,000 to 1. This means that for every kilogram of payload that returns to Earth, the mission must launch more than 1,000 kilograms of total mass from Earth's surface. 1,000 to 1. Consider what this ratio means in practical terms. If you want to bring back a single astronaut weighing 70 kilograms, you need to launch 70,000 kilograms of spacecraft and fuel. If you want to bring back a crew capsule weighing 10 tons, you need to launch 10,000 tons. The numbers become absurd almost immediately. A minimal crew capsule capable of supporting 4 astronauts through re-entry and landing weighs several tons. The Apollo command module weighed roughly 6 tons. Modern equivalents like the Orion capsule weigh approximately 11 tons. Adding life support systems capable of functioning for a decade adds more mass. Radiation shielding to protect the crew from Jupiter's lethal environment adds more mass. Scientific equipment to justify the enormous expense adds more mass. Spare parts for critical systems add more mass. Medical facilities for emergencies add more mass. A conservative estimate for the minimum return payload, the mass that actually comes back to Earth, reaches 20 to 30 tons. Multiply by the mass ratio. A minimal crewed round trip to Jupiter would require initial launch masses of 20 to 30,000 tons. For comparison, the Saturn V rocket had a total mass of approximately 3,000 tons fully fueled. The Space Launch System, currently under development, aims to deliver slightly more than 100 tons to orbit in its most powerful configuration. A Jupiter return mission would require launching the equivalent of 150 to 230 heavy-lift rockets worth of mass into orbit. This material would need to be assembled in space over years or decades of preparation. Fuel depots would need to store cryogenic propellants that boil away continuously unless kept at temperatures near absolute zero. Hydrogen, the most efficient chemical propellant, is notoriously difficult to store. It seeps through tank walls. It boils at temperatures just 20 degrees above absolute zero. Keeping it liquid for years in the thermal environment of space represents an unsolved engineering challenge. Crew modules would need to connect to propulsion stages through interfaces that function perfectly after years of waiting. Support equipment would need to survive the orbital environment without degradation. The entire assembly, larger than anything humans have ever built in space, would need to function as an integrated system, despite being constructed from hundreds of separately launched components. The total program cost would exceed anything humanity has ever attempted by orders of magnitude. The Apollo program cost approximately $200 billion in today's currency. A Jupiter return mission would cost trillions, potentially consuming entire national economies for decades, and this calculation assumes perfect efficiency, perfect execution, no mass growth from the inevitable engineering realities that make every space system heavier than its paper design. No mission changes from operational experience that reveals overlooked requirements. No system failures requiring spare parts beyond the planned inventory. No contingencies for problems nobody anticipated. Real engineering projects always grow heavier than initial estimates. The James Webb Space Telescope launched at roughly double its original mass estimate. The International Space Station required far more assembly flights than initially planned. Every spacecraft development program in history has experienced mass growth as designs matured and requirements clarified. A Jupiter mission would be no different, except that mass growth in a system already at the limits of possibility pushes the mission from impractical to impossible. This brings us back to the return problem. The outbound journey to Jupiter is achievable precisely because mission designers can ignore return requirements entirely. When the Galileo spacecraft launched in 1989 aboard the Space Shuttle Atlantis, it carried roughly 2,300 kilograms of scientific instruments, along with propulsion systems sized for one-way travel. The spacecraft used gravitational assists from Venus and Earth to reach Jupiter with fuel reserves that allowed orbital operations for years. If Galileo had been required to return those instruments to Earth, the launch mass would have increased by factors that placed it beyond any existing capability. The mission would have required multiple heavy-lift launches, orbital assembly, and technologies that did not exist then and barely exist now. Human missions must return their crew. This constraint transforms engineering challenges into physical impossibilities. Some proposals attempt to reduce delta-v requirements through extended use of gravitational assists. Instead of following direct transfer orbits that require enormous propulsion, spacecraft would loop through the inner solar system multiple times, stealing momentum from Venus or Earth or both, to reduce the velocity changes that onboard engines must provide. These gravity assists work beautifully for outbound missions. The Cassini spacecraft used 2 Venus flybys, an Earth flyby, and a Jupiter flyby before reaching Saturn in 2004. The trajectory took 7 years, but delivered the spacecraft to Saturn with fuel reserves that would have been impossible using direct flight. Messenger used 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys before entering Mercury orbit. The complex trajectory saved enormous amounts of fuel. For return missions, gravity assists create different problems entirely. Outbound gravity assists can be planned years or decades in advance. Mission designers know exactly where Venus and Earth will be during every possible launch window. They calculate intercept trajectories with comfortable margins. They build in course correction capability to compensate for small navigation errors. Return gravity assists must be timed from Jupiter's orbit, not from mission control centers on Earth. The planets are not arranged in convenient positions simply because a crew wants to come home. Return windows open only when Earth and Jupiter align, in configurations that permit efficient transfers with acceptable travel times. These favorable alignments occur infrequently. For direct returns without gravity assists, windows open approximately every 13 months, when Earth and Jupiter reach positions that minimize travel time and fuel requirements. Miss this window, and the crew waits over a year for the next opportunity while consuming supplies and accumulating radiation exposure. The 13-month period corresponds to the synodic period of Jupiter as seen from Earth, the time between successive oppositions when the 2 planets align on the same side of the Sun. A crew at Jupiter cannot simply decide to return when their supplies run low or systems begin failing. They must wait for the mathematics of orbital mechanics to permit their departure. If the optimal return window is 18 months away and their life support will fail in 12 months, they die waiting. If their radiation exposure is approaching lethal cumulative doses and the window is distant, they have no options except to watch their bodies absorb damage they cannot escape. Mission planners can partially address this constraint by launching during windows that guarantee favorable return opportunities. But these constraints drastically limit when missions can depart from Earth. Miss a launch window, and the mission waits many months for the next opportunity. Equipment designed for the missed window sits in storage, aging, becoming obsolete as technology advances. Crews trained for the mission must maintain readiness across extended time spans, and the gravitational assist trajectories that reduce fuel requirements also extend journey time substantially. An assist trajectory that loops through the inner solar system might require 5 or 6 years each direction, adding 2 to 6 years to total mission duration. The return problem grows worse with every year of extended travel. Longer missions require more consumables. Food for 6 astronauts consuming roughly 2 kilograms per person per day over 10 years totals, approximately 44,000 kilograms. Water consumption and recycling losses add more mass. Oxygen generation and carbon dioxide scrubbing require consumable materials that must be carried from Earth. Medical supplies for decade-long missions must anticipate every illness, injury, and emergency that might occur far from any hospital. Clothing wears out and must be replaced. Personal hygiene supplies accumulate. Every human need across a decade of living must be anticipated and loaded before departure. Every additional kilogram of consumables demands additional fuel to transport it. Under the brutal mass ratios that govern Jupiter missions, 10 tons of extra food requires approximately 10,000 tons of additional launch mass. The numbers spiral toward physical impossibility. Longer missions also expose systems to more degradation. Every mechanical seal has a rated lifetime, measured in cycles or years. Every filter accumulates contamination at rates that engineers can calculate but not prevent. Every electronic component experiences radiation damage that flips bits, corrupts memory, and eventually causes failures. The systems most critical for return are precisely those that accumulate the most degradation before they are needed. Every added safeguard makes the return harder. Consider radiation shielding. Jupiter's radiation environment requires substantial protection. Studies suggest 15 to 30 tons of shielding surrounding habitation areas. That shielding mass must be transported to Jupiter and back. Under the 1,000-to-1 mass ratio, 20 tons of radiation protection requires 20,000 tons of propellant and vehicle structure launched from Earth. Add redundant life support systems to improve survival probability. Add spare parts for components likely to fail. Add medical facilities, exercise equipment, psychological support systems. Each addition makes the crew more likely to survive. Each addition makes the launch mass more impossible to achieve. The launch mass climbs toward fantasy. The program costs escalate beyond any conceivable budget. The technological requirements exceed any demonstrated capability by margins that render the entire concept meaningless. And still the physics remain unsatisfied. Some proposals invoke nuclear thermal propulsion as a solution to the mass problem. Nuclear rockets can achieve higher exhaust velocities than chemical rockets, improving the mass ratio relationship. Humanity has actually tested nuclear thermal rockets. The NERVA program in the 1960s demonstrated engines that heated hydrogen propellant using nuclear reactors, achieving exhaust velocities roughly twice those of chemical rockets. The program was cancelled in 1972 for political and budgetary reasons, but the technology worked. Test firings demonstrated thrust levels and specific impulse values that confirmed theoretical predictions. Higher exhaust velocity means better mass ratios. Nuclear thermal propulsion could theoretically cut mass ratios by factors of 2 to 3 compared to chemical rockets. Cut a 1,000-to-1 mass ratio in half, and you have 500 to 1. Cut it by a factor of 3, and you have approximately 330 to 1. The mission remains impossible, just slightly less impossible. The mass ratios improve from absurd to merely outrageous. The launch requirements drop from hundreds of heavy lift equivalents to perhaps 50 or 100. The program costs decline from impossible to merely astronomical. The technological challenges shift from physically prohibited to merely unprecedented. Nuclear thermal propulsion does not solve the Jupiter return problem. More advanced nuclear propulsion concepts could theoretically achieve much higher performance. Nuclear pulse propulsion, studied in Project Orion during the 1950s and 60s, proposed propelling spacecraft using external nuclear bomb detonations. A series of nuclear explosions behind a massive pusher plate would accelerate the spacecraft to velocities that chemical and nuclear thermal rockets cannot approach. The physics actually work. Detailed engineering studies showed that nuclear pulse propulsion could achieve effective exhaust velocities 10 to 100 times higher than chemical rockets. Mass ratios for Jupiter missions would drop dramatically. A round trip might become theoretically feasible from a propulsion standpoint, but nuclear pulse propulsion faces barriers beyond physics. No nation has ever tested it. The engineering challenges of surviving repeated nuclear explosions remain unresolved. How do you build a pusher plate that survives thousands of nuclear detonations? How do you protect the crew from radiation produced by bombs exploding behind the spacecraft? How do you manufacture and store thousands of nuclear devices for the journey? The political barriers appear insurmountable in any foreseeable future. International treaties prohibit nuclear explosions in space. The Partial Test Ban Treaty of 1963 ended atmospheric nuclear testing and would need to be revised or abandoned before nuclear pulse propulsion could be developed. Public fear of nuclear technology makes funding impossible. The concept sits in technical literature, theoretically sound, practically abandoned. Ion propulsion offers another theoretical improvement. Ion engines accelerate charged particles using electric fields, achieving exhaust velocities 10 times higher than chemical rockets. Several spacecraft have successfully used ion propulsion for interplanetary missions, including the Dawn probe that visited the asteroids Vesta and Ceres. Ion engines have a critical limitation. They produce extremely low thrust. Chemical rockets generate millions of pounds of force, accelerating spacecraft rapidly through maneuvers that last minutes or hours. Ion engines generate fractions of an ounce of force, requiring months or years to accumulate the velocity changes that chemical rockets accomplish almost instantaneously. For Jupiter round trips, ion propulsion might reduce mass ratios while extending journey times to 15 or 20 years. The crew would spend 2 decades in space. Radiation exposure would approximately double compared to faster trajectories. System degradation would compound across timescales no spacecraft has ever operated. The probability of surviving the return journey would drop towards zero through mechanisms completely separate from propulsion efficiency. Ion propulsion trades one impossible problem for another impossible problem. There is no propulsion technology that exists or is seriously proposed that solves the fundamental mass-energy problem for Jupiter return missions. Some might argue that refueling at Jupiter could break the mass ratio trap entirely. The concept works elegantly for Mars. The Martian atmosphere contains abundant carbon dioxide that can be processed into methane and oxygen rocket fuels through well-understood chemistry. Water ice exists in Martian soil and polar caps. A spacecraft that lands on Mars with empty return tanks can theoretically refuel from local resources. This approach, called in situ resource utilization, has become central to Mars mission planning. Jupiter offers no such convenience. Jupiter itself has no solid surface. The planet is a ball of hydrogen and helium gas compressed to extreme densities by crushing gravity. No spacecraft can land on Jupiter. The planet has no ground, only progressively denser atmosphere that eventually transitions to liquid and then metallic hydrogen under pressures that would destroy any vehicle. Jupiter's moons contain water, ice, and other volatiles. Europa harbours an ocean beneath its frozen surface. Ganymede and Callisto contain substantial ice deposits, but extracting and processing these resources requires industrial infrastructure that must itself be transported from Earth. Mining equipment must be delivered. Processing plants must convert raw ice into propellants. Storage facilities must keep cryogenic fuels from boiling away. The mass of fuel production equipment might equal or exceed the mass of simply carrying return propellant directly. The engineering complexity of operating automated industrial facilities on radiation-blasted moons introduces failure modes that do not exist for missions carrying their own fuel. What happens if the mining equipment breaks down? What happens if the processing plant produces contaminated fuel? What happens if storage tanks leak? Refueling at Jupiter does not solve the mass problem. It transforms the mass problem into a logistics problem, while adding operational complexity that increases mission failure probability. Getting there was never the real challenge. The outbound journey to Jupiter is energetically expensive but achievable through straightforward application of existing technology. Carry enough fuel. Follow efficient trajectories, except that no return capability exists. The return journey demands capabilities that current technology cannot provide, and future technology shows no clear path to achieving. The energy requirements exceed what chemical rockets can deliver. Nuclear alternatives remain undeveloped or politically impossible. And energy is not the only barrier. The years required for any Jupiter round trip expose crews and equipment to conditions that compound every other failure mode. Radiation accumulates, systems degrade, human bodies weaken. The return vehicle that successfully reached Jupiter becomes increasingly unreliable with every passing month. This cascade of failures forms the subject of the next section. The mass-energy relationship establishes the foundation of impossibility. Time and environment build upon that foundation until the mission collapses completely. Time destroys everything. This truth operates so slowly on Earth that humans rarely notice it. Mountains erode grain by grain across millions of years. Continents drift centimeters per decade. Rivers carve canyons through processes that span geological epochs. Even human-built structures endure for centuries when maintained. The Pantheon in Rome has stood for nearly 2,000 years. Medieval cathedrals still host services after 700 years of continuous use. Ancient aqueducts continue to carry water in some parts of the world. This terrestrial patience creates dangerous assumptions about what machines can endure. Space does not share Earth's gentle timeline. The void accelerates destruction through mechanisms that tear apart equipment designed for Earthbound conditions. Every protective layer that Earth provides vanishes the moment a spacecraft leaves the atmosphere. Every assumption about material behavior, electronic reliability, and biological stability must be recalculated for an environment that actively dismantles anything humans build. The vacuum itself attacks spacecraft continuously. On Earth, atmospheric pressure pushes inward on sealed containers, helping maintain their integrity. In space, the pressure differential reverses. Internal atmosphere pushes outward against seals never designed for such sustained stress. Materials that hold together under atmospheric pressure may slowly fail in vacuum. Volatile compounds evaporate from lubricants and sealants. Outgassing degrades surface properties and contaminates sensitive instruments. Temperature swings compound the stress on materials. In sunlight, spacecraft surfaces can reach temperatures exceeding 250 degrees Fahrenheit. In shadow, those same surfaces plunge to negative 200 degrees or colder. This cycling continues across years as the vehicle rotates to distribute solar heating, passing components from baking illumination to freezing darkness thousands of times during the journey. At Jupiter's distance from the Sun, solar heating diminishes but does not disappear, and spacecraft still experience thermal cycling as they rotate or pass through planetary shadows. Thermal cycling fatigues materials at molecular scales. Metal crystalline structures develop microscopic cracks that grow with each cycle. Polymer seals harden and become brittle as plasticizers evaporate in vacuum. Adhesives that bonded components firmly during manufacture gradually lose their grip as thermal stress breaks chemical bonds. Lubricants that allowed smooth mechanical operation thicken or evaporate depending on their composition and the temperatures they experience. Radiation compounds this degradation through entirely separate mechanisms. Charged particles from the Sun and cosmic rays from distant stellar explosions bombard everything in space with energies that scramble electronics and damage biological tissue. Earth's magnetic field deflects most of this radiation, creating a protective bubble that extends tens of thousands of kilometers into space. Beyond this magnetosphere, spacecraft and their crews absorb radiation doses that accumulate toward dangerous thresholds. Solar radiation fluctuates with the 11-year solar cycle, and with unpredictable solar flares that can increase particle fluxes by factors of thousands within hours. Cosmic rays arrive from every direction, their sources the violent deaths of massive stars throughout the galaxy. These particles carry energies that no practical shielding can completely stop. Some penetrate any barrier humans can construct. Micrometeorites add kinetic damage to the chemical and radiological assault. These particles, some smaller than grains of sand, travel at velocities measured in kilometers per second. At such speeds, even tiny objects carry enough energy to puncture thin materials or erode protective coatings over time. The longer a spacecraft operates in space, the more impacts it accumulates. Each impact slightly degrades hull integrity, scratches optical surfaces, and damages thermal protection systems. The International Space Station demonstrates that long-duration space habitation is possible despite these challenges. Crews have occupied the station continuously for over 2 decades. Systems function reliably enough to support human life, approximately 250 miles above Earth's surface. This achievement represents humanity's most successful experiment in extended space operations, but the station survives through advantages that Jupiter missions cannot replicate. Resupply missions arrive every few weeks, bringing fresh food, replacement components, and new equipment. When systems fail, astronauts can install new parts delivered from Earth. When consumables run low, the next cargo vehicle restores supplies. When equipment ages past its useful life, replacements arrive on the next scheduled flight. The station exists within a constant flow of material support that makes long-duration operation sustainable. The station also orbits close enough to Earth that evacuation remains possible. Astronauts who develop medical emergencies can board return vehicles and reach hospitals within a day. Those who suffer psychological breakdowns can be brought home before their conditions worsen. The proximity to Earth provides a safety net that catches failures before they become fatal. The psychological toll of long-duration spaceflight remains poorly understood because no human has experienced confinement at the scales a Jupiter mission demands. The longest continuous spaceflight in history lasted 437 days, when Russian cosmonaut Valery Polyakov remained aboard the Mir space station from January 1994 to March 1995. Polyakov demonstrated that humans can survive in weightlessness for extended periods without catastrophic physical decline. His mission provided invaluable data about physiological adaptation to spaceflight. But Polyakov could see Earth outside his window every 90 minutes as the station orbited. He could speak with family through communication links that connected within seconds. He knew that emergency return remained possible if his mental state deteriorated beyond recovery. The psychological safety net never disappeared entirely. A Jupiter crew possesses none of these anchors. Earth shrinks from a blue marble to a pale dot to an invisible point lost among countless stars. The familiar world that every human being has known since birth vanishes. The crew cannot point toward home, because home has become indistinguishable from the background of space. This visual disconnection from Earth has never been experienced by any human being beyond the brief Apollo missions to the Moon. Communication delays transform conversations with loved ones into exchanges of recorded messages. A spouse asks a question. The astronaut responds. The spouse receives that response more than an hour later and replies with another message. 2 hours pass for a single exchange that would take seconds on Earth. Conversations lose their rhythm. Emotional connection attenuates across delays that make spontaneous interaction impossible. Ground-based isolation studies provide troubling hints about what extended confinement produces. The Mars 500 experiment confined 6 volunteers in a simulated spacecraft for 520 days between 2010 and 2011. Researchers monitored psychological states throughout the mission. By the experiment's midpoint, crew members exhibited disturbed sleep patterns, reduced activity levels, and withdrawal from social interaction. One crew member spent most of his time in his compartment, avoiding contact with others. Interpersonal tensions emerged despite careful crew selection and psychological screening. This experiment lasted less than 2 years, with participants who could abort at any time, who knew they remained on Earth, who faced no actual danger. A Jupiter mission lasts 5 times longer with crews who cannot abort, who float hundreds of millions of miles from home, who understand that system failures mean death. Psychological research identifies a phenomenon called third quarter syndrome. isolated groups often experience their lowest morale and highest conflict roughly 3/4 through their confinement. For Antarctic winter-over crews, this occurs around August. For submarine deployments, it occurs in the final months before returning to port. For a Jupiter crew, the third quarter falls during the return journey. Precisely when psychological resilience matters most. Precisely when system reliability has degraded furthest. Precisely when accumulated, radiation exposure has begun manifesting symptoms. The crew faces their darkest psychological period, while operating spacecraft that have aged beyond design specifications, using bodies weakened by years of weightlessness and radiation, knowing that Earth remains years away. The compounding is not coincidental, it is inevitable. At Jupiter, none of these safety margins exist. A spacecraft traveling to Jupiter and back operates for a decade or more, with zero possibility of resupply. Every component, every spare part, every consumable required for the entire mission must be loaded before departure. If supplies run short, no cargo vessel can deliver more. If critical systems fail beyond the repair capability of carried spares, no replacement arrives. The crew either fixes problems with resources already aboard, or dies from the consequences. Evacuation is not merely difficult at Jupiter distances. It is physically impossible. Even if a rescue mission launched the moment an emergency began, travel time measured in years would render any rescue meaningless. A crew facing life support failure at Jupiter cannot wait 3 years for help. A crew member suffering a medical emergency cannot be transported to Earth before conditions deteriorate beyond treatment capability. This isolation transforms every system failure from an inconvenience into a potential death sentence. The reliability mathematics become terrifying when applied to decade-long missions. Engineers measure system reliability as the probability that a component will function correctly over a specified time period. A reliability of 99% over 1 year means that in 100 identical systems operating for 1 year each, approximately 1 will fail. This sounds reassuringly high. That same system with 99% annual reliability has roughly 90% reliability over 10 years. The mathematics is not linear. Failure probability compounds as time extends because each year presents new opportunities for the system to malfunction. A spacecraft operating in the Jupiter environment contains dozens of systems that must all function correctly for the crew to survive. Atmospheric processing must continue working to remove carbon dioxide and maintain oxygen levels. Water recycling must not fail, or the crew will dehydrate within days. Power generation must remain operational to run every other system. Thermal regulation must keep temperatures within the narrow band that humans and electronics require. Navigation must provide accurate positioning to enable the return trajectory. Propulsion must respond when commanded for course corrections and the critical return burns. If 30 critical systems each have 90% reliability over the mission duration, the probability that all 30 function perfectly throughout is approximately 4%. 4 chances in 100 that everything works correctly. 4% mission success is not acceptable risk by any standard ever applied to human spaceflight. It is near certain death disguised by mathematics that sound reassuring when applied to individual components, but devastating when combined across complete systems. Mission designers address this through redundancy. Where one system might fail, include 2. Where 2 might fail, include 3. Triple redundancy for critical systems means that 2 independent failures must occur before capability is lost. Triple redundancy improves the mathematics substantially. If each of 3 redundant systems has 90% reliability, the probability that all 3 fail drops below 1%. Mission success probability climbs toward levels that might be acceptable. But redundancy introduces complications that erode its theoretical benefits. More systems mean more opportunities for unexpected interactions between components. A failure in one system might stress a backup system in ways designers never anticipated. Electrical shorts can cascade through redundant circuits. Software bugs can affect all instances of a program simultaneously. Common mode failures, where a single cause defeats all redundant systems, represent a category of risk that redundancy cannot address. More connections mean more potential points of failure at interfaces. Every electrical connector, every fluid coupling, every mechanical joint represents a location where failure can occur. Tripling the number of systems triples the number of interfaces, potentially tripling the opportunities for connection failures. More complexity means more difficulty diagnosing problems when they occur. A crew facing a system anomaly must determine which of multiple redundant systems is malfunctioning. Troubleshooting becomes exponentially more difficult as system complexity increases. Time spent diagnosing problems is time not spent on other critical activities, and some systems cannot be meaningfully redundant regardless of mass budget. The pressure vessel containing crew atmosphere represents a single point of failure that no backup can address. If the hull breaches significantly, the crew dies regardless of how many spare components sit in storage. You cannot carry a backup hull. The primary structure either maintains integrity or it does not. The radiation environment of Jupiter deserves particular attention because it represents a threat unlike anything humans have faced in space. Jupiter possesses the most intense radiation environment of any planet in the solar system. Its magnetic field, generated by currents in the planet's metallic hydrogen interior, is approximately 20,000 times stronger than Earth's field. This immense magnetic strength traps charged particles from the solar wind and accelerates them to energies that would kill unprotected humans within hours of exposure. The Jovian magnetosphere extends millions of kilometers into space, creating radiation belts that dwarf their terrestrial counterparts. Earth's Van Allen belts, which concerned mission planners during the Apollo program, pale in comparison to the particle densities and energies found near Jupiter. The Apollo astronauts traversed Earth's radiation belts quickly, minimizing exposure. No quick transit is possible through Jupiter's radiation environment for missions intending to operate in the Jovian system. At the orbit of Io, Jupiter's innermost large moon, radiation doses reach approximately 3,600 rems per day. For context, a dose of 400 rems delivered over a short period causes acute radiation syndrome with approximately 50% mortality. Symptoms include severe nausea, catastrophic immune suppression, internal bleeding, and multiple organ failure. A human at Io's orbital distance without shielding would receive lethal exposure within hours, not days. The outer Galilean moons orbit in progressively less intense radiation environments. At Europa, approximately 417,000 miles from Jupiter, doses reach roughly 540 rems per day. This remains extraordinarily dangerous. Even with substantial shielding, crews operating near Europa would accumulate concerning exposures within weeks. Extended operations would push cumulative doses toward levels that guarantee long-term health consequences and potentially acute effects. At Ganymede and Callisto, radiation levels decrease further. Callisto orbits far enough from Jupiter that radiation levels become manageable with appropriate shielding. Mission concepts that propose human operations in the Jupiter system typically focus on Callisto for this reason, despite its greater distance from the scientifically interesting inner moons. A spacecraft operating anywhere in the Jupiter system must protect its crew from radiation levels that exceed anything human technology has routinely managed. Shielding options exist. Water absorbs charged particles effectively, and could theoretically surround habitation modules in tanks that serve double duty as radiation protection and consumable storage. Polyethylene and other hydrogen-rich plastics block radiation more effectively per unit mass than metals. Specialized materials developed for radiation environments offer further improvements, but effective shielding requires substantial mass. Studies conducted by NASA and independent researchers suggest that adequate radiation protection for crews operating in the Jupiter system requires shielding masses of 15 to 30 tons surrounding habitation areas, depending on how close to Jupiter operations occur and how long exposure continues. This estimate assumes operations at the orbit of Callisto or beyond. Missions targeting Europa would require substantially more shielding or would accept rapidly accumulating doses, but shielding mass addresses only the acute exposure problem. A more insidious threat comes from cumulative dose accumulation over mission duration. Even with excellent shielding, some radiation penetrates. High-energy particles that individual atoms of shielding fail to stop continue through to crew areas. Secondary radiation produced when particles interact with shielding material adds to the background exposure. Cosmic rays with energies beyond what any practical shield can fully block occasionally strike human tissue. Over a decade-long mission, these small doses accumulate. Every day adds to the running total. Every month pushes the cumulative exposure higher. Every year brings astronauts closer to thresholds beyond which damage becomes inevitable. Current NASA guidelines restrict astronaut career radiation exposure to levels designed to keep excess cancer risk below approximately 3%. A Jupiter round trip would likely exceed these limits substantially, even with aggressive shielding and operational caution. Crews would return to Earth, if they returned at all, facing elevated cancer risks for the remainder of their lives. But radiation does not only cause cancer. Acute radiation syndrome represents a more immediate threat. This condition begins at exposures above roughly 100 REMs delivered over short periods. Symptoms progress from nausea and weakness through severe immune suppression to bone marrow failure and death depending on dose severity. If shielding fails during a radiation storm, crew members could receive acutely dangerous exposures within hours. Jupiter's radiation environment fluctuates with solar activity and internal magnetospheric dynamics. Intensification events can multiply radiation levels for periods lasting days. A crew caught in deteriorating conditions without adequate shelter faces rapid health decline that no medical intervention can reverse. Radiation damages equipment as effectively as it damages biology. Memory cells flip from ones to zeros or zeros to ones at random. Processor logic becomes unreliable as accumulated damage corrupts circuit behavior. Sensors that provided accurate data when new deliver increasingly erratic readings. Spacecraft designers address this through radiation hardening, special manufacturing processes that increase component resistance to charged particle damage. Hardened electronics use larger transistor geometries, redundant circuit pathways, and error correction algorithms that detect and fix radiation-induced faults. But radiation hardening provides protection, not immunity. Even hardened electronics accumulate damage over years of exposure. The return propulsion system, the navigation computers, the life support controllers all become less reliable precisely when the crew needs them most. Now, consider life support. Human beings require atmospheric oxygen, liquid water, digestible food, and temperature regulation to survive. On Earth, these necessities arrive automatically through planetary systems that have operated for billions of years. In space, every requirement must be provided by mechanical and chemical systems that operate continuously without interruption. The International Space Station demonstrates that closed-loop life support is achievable for extended periods. Water recycling systems recover approximately 90% of crew urine and humidity from cabin air. Carbon dioxide scrubbers remove exhaled gas from the atmosphere. Oxygen generation systems electrolyze water to replenish breathable air. These systems require constant maintenance to function reliably. Filters that remove particulates from the air become clogged with debris and must be replaced. Membranes that separate water from waste contaminants degrade as dissolved minerals and organic compounds accumulate on their surfaces. Pumps that circulate fluids develop bearing wear and seal degradation. Chemical beds that react with carbon dioxide become exhausted as their reactive capacity is consumed. On the station, resupply missions deliver replacement components regularly. Fresh filters arrive. Spare pump assemblies wait in inventory. The constant flow of material from Earth keeps life support functioning, despite the degradation that continuous operation causes. The station's maintenance history illustrates how frequently critical systems fail even in relatively benign conditions. In July 2010, an ammonia pump module in the station's cooling system failed without warning. The thermal control system could no longer regulate temperatures across half the outpost. Astronauts faced potential overheating of critical electronics within days. NASA launched emergency spacewalks to replace the failed module using spare parts already aboard. The repair succeeded. The oxygen generation system has experienced multiple failures, requiring component replacements delivered from Earth. Toilets have failed, creating sanitation emergencies resolved only through resupply missions carrying replacement hardware. Every one of these failures would have been fatal at Jupiter. No spare pump module waits in a cargo vehicle 3 days away. No emergency resupply addresses unexpected breakdowns. The crew either carries every possible replacement or accepts that certain failures end the mission permanently. At Jupiter, no resupply arrives. Every filter, membrane, pump component, chemical bed, and maintenance tool required for a decade of operation must be loaded before departure. The manifest must anticipate consumption rates, failure probabilities, and maintenance requirements across time spans far exceeding any operational experience. If the manifest proves insufficient, the crew faces life support degradation with no remedy available. Food presents a mass problem with no elegant solution. Complete recycling of food waste back into edible nutrients remains beyond current technology despite decades of research. The chemical complexity of human nutrition defies simple mechanical processing. Space-based agriculture offers theoretical advantages, but practical challenges. Plants require growth chambers with controlled lighting, temperature, humidity, and nutrient delivery. The mass of agricultural systems capable of feeding a crew exceeds the mass of preserved food for missions shorter than several years. Current mission planning therefore assumes crews carry their food rather than grow it. A crew of 6 consuming roughly 2 kilograms of food per person per day requires approximately 44,000 kilograms of food for a 10-year mission, plus packaging, preparation equipment, and storage systems that prevent spoilage. The crew that departs Earth represents healthy, well-trained, psychologically stable individuals, selected through rigorous screening from thousands of qualified applicants. They have passed extensive physical examinations. They have demonstrated resilience under stress. They have practiced for years to handle emergencies. The crew that attempts to return from Jupiter will be fundamentally different people. Years of weightlessness have transformed their bodies in ways that Earth-based medicine struggles to address. Bones have lost density at rates of 1 to 2% per month, despite hours of daily exercise on equipment designed to apply mechanical loads. Over a multi-year mission, the cumulative loss leaves skeletons weakened beyond anything ground medicine has routinely treated. Vertebrae compress. Hip joints deteriorate. The risk of fractures upon return to gravity becomes substantial. Muscles have atrophied despite resistance training protocols. The mechanical loads that maintain muscle mass on Earth cannot be fully replicated in weightlessness. Cardiovascular systems have adapted to pumping blood in zero gravity, where no hydrostatic column demands pressure to lift fluid from feet to brain. Hearts become less efficient. Blood vessels lose tone. Return to Earth's gravity will stress cardiovascular systems weakened by years of reduced workload. Immune systems have been compromised by radiation exposure and the chronic stress of long-duration spaceflight. Studies show that immune function declines in space through mechanisms not fully understood. White blood cell counts drop. Antibody production diminishes. Minor infections that healthy bodies would suppress quickly become serious medical concerns. Vision may have degraded through intracranial pressure changes caused by fluid shifts in weightlessness. Many astronauts returning from station missions report vision problems that sometimes persist for months or years after landing. The mechanism involves cerebrospinal fluid pressing on optic nerves, potentially causing permanent damage. Psychological states have been affected by years of isolation and confinement in spaces smaller than most apartments. Communication delays make real-time conversation with Earth impossible. The constant knowledge that no rescue is possible weighs on minds for years. Depression, anxiety, interpersonal conflicts, and cognitive decline have all been documented in isolated environments far less extreme than a decade-long Jupiter mission. These degraded humans must operate spacecraft systems that have similarly degraded, making decisions during emergencies that exceed anything they trained for. With equipment performing outside its design specifications, receiving advice that arrives more than an hour after they ask for it. Every kilogram added to address one problem feeds back into the mass energy problem that underlies all other problems. Medical supplies add mass, psychological support systems add mass, exercise equipment adds mass, radiation shielding adds mass. The cascade is self-reinforcing. Solutions create problems that demand additional solutions. The mission architecture does not converge toward a viable design point where all requirements are satisfied simultaneously. It diverges toward impossibility, as each added safeguard demands further additions. Some might argue that technological progress will eventually solve these problems. Better materials might reduce shielding mass. Improved recycling might reduce consumable requirements. Advanced medicine might address crew health decline. These improvements might make the mission marginally less impossible. They do not make it possible. The fundamental constraints are physical, not technological. The distance to Jupiter establishes minimum travel times that cannot be reduced below approximately 2 years, each direction without propulsion systems that do not exist. The radiation environment of Jupiter exists regardless of human technology, generated by planetary magnetic fields that cannot be turned off. The rocket equation governs mass relationships with mathematical precision that no material science advances can circumvent. Progress nibbles at the margins of impossibility, while the core barriers remain intact. The return vehicle that departs Jupiter must carry a crew weakened by years of spaceflight through a journey lasting additional years, using systems degraded by nearly a decade of operation. It must execute complex maneuvers with precision that leaves no margin for error. It must survive re-entry into Earth's atmosphere, using thermal protection systems that have aged beyond any demonstrated reliability. The probability that all of these requirements are simultaneously met approaches zero as mission duration extends and complexity increases. This is the mathematical consequence of compounding failure probabilities, accumulating degradation, and cascading mass requirements, and the mathematics does not negotiate. Somewhere between Earth and Jupiter, the mission stops being difficult and becomes impossible. The boundary is not marked by a specific distance in miles or a particular duration in years. It emerges gradually from the accumulating weight of requirements that cannot all be satisfied simultaneously. Each individual constraint appears manageable when examined in isolation. Together, they form a web that tightens around any proposed mission architecture until nothing viable remains. The mass-energy cascade makes every requirement compete with every other. Something must be removed from the design to make the numbers work. Remove shielding and the crew dies from radiation exposure during Jupiter operations. Remove fuel and the crew cannot generate the velocity changes required for return. Remove crew members and the mission loses the operational capability and psychological stability that minimal staffing provides. Remove redundant systems and single component failures become fatal events with no backup. There is no configuration that satisfies all requirements simultaneously. This conclusion frustrates people who believe technology solves all problems eventually. They point to achievements that seemed impossible before they happened. Humans walked on the moon using computers less powerful than modern calculators. Reusable rockets now land on drone ships after boosting payloads to orbit. Spacecraft have visited every planet in the solar system and continue operating decades after launch. Human technological progress has repeatedly achieved goals that previous generations considered impossible dreams. These achievements share a common characteristic that Jupiter return missions lack. They all involved expanding human capabilities within physical limits, rather than attempting to exceed those limits entirely. The Moon is close enough to reach with chemical rockets because the velocity requirements fall within what the rocket equation permits for reasonable mass ratios. The journey takes 3 days, allowing life support systems to function within their design margins. Communication delays measure in seconds, permitting real-time coordination with ground controllers. The entire mission from launch to splashdown spans approximately 8 days, short enough that system degradation remains negligible and crew health decline barely begins. Reusable rockets exploit atmospheric conditions unique to Earth. The atmosphere provides drag that helps slow descending boosters without requiring additional fuel. Grid fins and engine restarts work because Earth's atmosphere is thick enough to provide aerodynamic control at landing speeds. This technology represents brilliant engineering within the constraints that Earth's environment provides. It does not transcend those constraints. Try to land a booster on the Moon using the same techniques, and it fails completely because there is no atmosphere to provide drag or aerodynamic control. Planetary flybys require only that spacecraft survive long enough to collect data during brief encounters. The spacecraft carried no return fuel, no radiation shielding for human occupants, no life support systems that must operate for decades. Voyager was designed to die in the outer solar system after completing its observations. It is still operating 47 years after launch, precisely because it carries no burden of return requirements. A crewed return from Jupiter requires capabilities that exceed physical limits in ways these other achievements did not. The speed of light establishes a communication delay that prevents real-time assistance from Earth. Controllers cannot help crews solve problems faster than the hour-plus round-trip signal time permits. This is not a technology limitation. It is a fundamental property of the universe that no engineering can circumvent. The rocket equation governs mass relationships with mathematical precision that no propulsion technology can escape. More efficient engines improve the numbers, but cannot eliminate the exponential relationship between velocity change and fuel mass. Even theoretically perfect engines that convert mass to energy with 100% efficiency must still obey conservation of momentum. Radiation effects on biology follow from nuclear physics that operates identically regardless of human wishes. Charged particles damage DNA and cellular machinery through mechanisms that shielding can reduce but never eliminate entirely. The cross-section for particle interaction with biological material is set by quantum mechanics, not human preference. Human metabolic requirements derive from biochemistry that evolution optimized for Earth conditions over billions of years. Bodies need oxygen, water, calories, and gravity in quantities and forms that cannot be arbitrarily reduced without killing the organism. These requirements are not design choices that engineers can optimize away. No amount of engineering progress changes these underlying constraints. Technology can work more efficiently within the constraints, extracting more performance from each kilogram of mass, each watt of power, each gram of propellant. Technology cannot eliminate the constraints themselves. Consider the most optimistic scenario that remains within plausible technological development. Advanced nuclear thermal propulsion achieves specific impulse values, double those of chemical rockets, reducing mass ratios by a factor of 3 to 5. This represents the upper bound of what nuclear thermal technology might deliver, based on experimental programs conducted in the 1960s and theoretical analyses conducted since. The technology is not science fiction. It has been demonstrated in ground tests. Developing it for spaceflight would require decades of engineering effort and substantial funding, but the physics is understood. Revolutionary life support recycling achieves 98% closure, meaning 98% of water and atmospheric components are recovered and reused. This cuts consumable mass requirements roughly in half compared to systems achieving 90% closure, which represents current technology limits. Such improvement would require breakthroughs in membrane technology, biological processing, and system reliability. Breakthrough materials reduce radiation shielding mass by 40% while maintaining equivalent protection. Advanced composites, hydrogen-rich polymers, or exotic materials not yet invented might achieve this improvement through better stopping power per unit mass. Improved reliability engineering doubles system design lifetimes through better manufacturing processes, more robust components, and superior quality control. Systems designed for 5 years of operation now function reliably for 10 years. All of these advances together, if achieved simultaneously, might reduce mission impossibility from absurd to merely impractical. The launch mass drops from hundreds of thousands of tons to perhaps 50,000 tons, still equivalent to dozens of heavy-lift rockets, still requiring orbital assembly infrastructure that does not exist, still demanding budgets measured in hundreds of billions of dollars. The survival probability rises from negligible to merely unacceptable. Instead of 4% mission success, perhaps 20% becomes achievable, still meaning that 4 out of 5 crews die, still representing odds that no astronaut selection board would accept and no space agency would propose to funders. The mission remains beyond realistic planning horizons, even with technological improvements that may never materialize. Some proposals attempt to solve the mass problem through distributed architecture. Robotic precursor missions would pre-position supplies at Jupiter years before any crew departs Earth. Fuel depots, spare parts, food caches, and replacement equipment would wait in Jupiter orbit for the crewed vehicle to arrive. The crewed spacecraft would launch lighter, knowing that essential supplies await at the destination. Upon arrival, the crew would rendezvous with pre-positioned assets, refuel from waiting propellant, and return using resources delivered separately from their own vehicle. This architecture distributes the mass problem across multiple launches, rather than eliminating it. Every kilogram of supplies positioned at Jupiter must still be launched from Earth using the same unfavorable mass ratios that apply to crewed vehicles. The total program mass remains similar to single launch approaches. The total program cost remains astronomical. The timeline extends across decades as precursor missions launch, travel to Jupiter, enter orbit, and verify their systems remain functional before any crew can safely depart. And pre-positioned supplies create new failure modes that single-vehicle missions avoid. The fuel cache must survive years of waiting in the Jupiter radiation environment. Propellant storage systems must prevent boil-off of cryogenic fluids across time spans that exceed all demonstrated capability. Hydrogen, essential for high-efficiency propulsion, seeps through container walls and boils at temperatures just above absolute zero. Maintaining liquid hydrogen for years in the Jupiter environment represents an unsolved engineering challenge. The rendezvous between crewed vehicle and supply cache must succeed, despite communication delays that prevent real-time navigation assistance. The crew must locate assets positioned years earlier, using navigation systems that have accumulated their own errors during years of operation. Docking must proceed without the ground support that enables rendezvous operations in Earth orbit. The supplies must remain usable after years of storage in conditions that degrade everything humans build. Food must not spoil despite years of radiation exposure and temperature cycling. Mechanical components must not seize from disuse. Electronics must not fail from accumulated radiation damage. Every system in the pre-positioned cache must function perfectly after years of dormancy in an environment more hostile than any storage facility on Earth. If the fuel cache fails before the crew arrives, the mission fails. The crew reaches Jupiter with insufficient propellant for return and no alternative supply source. If the rendezvous misses due to navigation errors or mechanical failures, the mission fails. The crew watches their supplies drift away into Jupiter orbit, while their own vehicle lacks the propellant to chase them down. If the supplies have degraded beyond usefulness after years of waiting, The mission fails. The crew docks with a cache of spoiled food, failed electronics, and contaminated fuel that cannot power their journey home. Pre-positioning does not reduce mission risk. It introduces additional failure modes while distributing mass requirements across longer timelines and larger budgets. The fundamental constraints remain unsatisfied. The return problem persists, regardless of how many launches spread the mass across the solar system. Others propose abandoning the return requirement entirely through generation ships. Crews would accept that the voyage consumes their entire lives, with children born during transit and descendants eventually completing a mission their ancestors began. This does not solve the return problem. It redefines the mission as one-way colonization rather than exploration and return. Calling a generation ship a solution is like calling walking a solution to the problem of supersonic flight. Generation ships also face their own impossibility barriers. Population genetics demands several hundred individuals to maintain genetic diversity scaling. Crew size by factors of 50 multiplies every mass requirement proportionally. Social stability across generations in complete isolation has never been tested in human history. Resource recycling must function for lifetimes, not years, requiring the vessel to become a self-sustaining industrial civilization. Generation ships multiply the problems rather than solving them. Still other proposals invoke technologies that do not exist and may never prove possible. Suspended animation could theoretically pause crew metabolism, reducing consumable requirements to near zero and eliminating psychological stresses from conscious confinement. If humans could be safely frozen and revived, crews might sleep through the journey, awakening only at Jupiter and again upon Earth arrival. No suspended animation technology exists. Cryogenic preservation kills human tissue through ice crystal formation that ruptures cell membranes. Chemical approaches to metabolic suspension remain in early research stages with no demonstrated path to human application. Despite decades of science fiction depicting suspended animation, actual progress toward the capability has been minimal. Suspended animation appears in stories because writers can ignore biological barriers that actual engineers cannot circumvent. Other proposals invoke technologies that do not exist and may never prove possible. Suspended animation, exotic physics, fully autonomous AI. These either lack any experimental foundation, remain decades from human application, or concede that humans cannot make the journey rather than solving the return problem. None of these proposals represents a path to crewed round trips. The fundamental problem resists solution because it emerges from multiple independent constraints that must all be satisfied simultaneously. Solving the mass problem through better propulsion does not solve the radiation problem that requires shielding mass. Solving the radiation problem through operational distance from Jupiter does not solve the timeline problem that extends mission duration and system degradation. Solving the timeline problem through faster trajectories requires more fuel mass that worsens the mass problem. Any solution that addresses one constraint tends to worsen others. Faster trajectories require more delta V, which requires more fuel, which adds more mass. More shielding provides better radiation protection, but adds mass that requires more fuel. Longer missions allow more favorable trajectories with lower fuel requirements, but extend system degradation and radiation exposure. Shorter missions reduce degradation and exposure, but demand propulsion capabilities that do not exist. The constraints form a web where pulling on any strand tightens others. There is no thread to pull that loosens the entire structure. This is why space agencies do not seriously propose crewed Jupiter missions. NASA's long-term planning documents discuss Mars exploration in extensive detail. They describe technology development programs, mission architectures, timeline projections, and budget estimates. They analyze risks, propose mitigation strategies, and identify capability gaps that research programs must address. Mars represents an enormous challenge that NASA believes can be met through sustained effort and adequate funding. The same documents mention Jupiter only as a destination for robotic science missions. Crewed Jupiter exploration appears nowhere in official planning, not because planners lack imagination, but because engineering analysis reveals no viable path forward. The absence is not oversight. The absence reflects engineering reality that public communications rarely make explicit. Humans can reach the moon and return. This has been demonstrated 12 times with 6 successful landings. Humans can probably reach Mars and return. This will likely be demonstrated within coming decades if programs proceed as planned. The challenges are severe but not insurmountable. The risks are high but potentially acceptable. Humans cannot reach Jupiter and return regardless of cost or risk tolerance. This limitation derives from physical constraints that interact to produce requirements exceeding what any realistic technology can provide. Consider what happens to a crew that successfully reaches Jupiter against all odds. Their vehicle entered Jupiter orbit after 3 years of flawless operation. Every system functioned within specifications, despite years of exposure to deep space conditions. Every crew member remained healthy, despite radiation, isolation, and physiological stress. Every navigation maneuver executed precisely. Threading gravitational assists and trajectory corrections to arrive at the planned destination on schedule. They have achieved something unprecedented in human history. They float farther from Earth than any humans have ever traveled, farther than any humans may ever travel again. Jupiter fills their viewports, its bands of swirling clouds stretching across a disk 11 times wider than Earth. The great red spot rotates into view, a storm system that has raged for centuries, large enough to swallow their home planet with room to spare. They conduct their science program with the diligence of researchers who understand they are humanity's first and perhaps only witnesses to these sights at close range. They observe Jupiter's moons through instruments calibrated for proximity observations impossible from Earth. Europa's ice shell reveals fractures and chaos terrain hinting at the ocean below. Ganymede's magnetic field interacts with Jupiter's field in ways that ground-based telescopes could never resolve. Io's volcanoes erupt constantly, painting the moon's surface with sulfur compounds in yellows and reds. They collect data that will transform human understanding of the outer solar system for generations. They send reports that arrive at Earth 35 to 50 minutes after transmission, depending on orbital positions. For a brief period, they are the most celebrated humans alive. And then they begin preparing for return. The return propulsion system has been dormant for 3 years. Its engines have not fired since the Jupiter orbit insertion burn that concluded the outbound journey. Its fuel tanks have maintained cryogenic propellants at temperatures near absolute zero through years of thermal management. Its control systems have waited in standby mode while radiation bombarded their circuits continuously. The system must now ignite flawlessly. The crew's lives depend entirely on propulsion performance that cannot be tested until the actual departure burn begins. If engines fail to start, no repair is possible. If thrust falls short of requirements, no correction exists. If tanks have developed leaks or pumps have seized or valves have failed, the crew discovers these problems only when the systems are needed and cannot be fixed. If propulsion fails to perform, the crew remains at Jupiter until their supplies run out. They watch their life support consumables dwindle day by day, knowing that no rescue can reach them, no resupply will arrive, no alternative transportation exists. They die slowly in the most remote location any humans have ever occupied. The return trajectory requires precise timing that orbital mechanics dictates regardless of spacecraft readiness. The launch window opens for a period measured in weeks, when Earth and Jupiter align in configurations that permit efficient transfers. If the propulsion system requires troubleshooting beyond the window duration, if navigation errors accumulate that must be corrected before departure is safe, if unexpected malfunctions demand repairs that extend the timeline, the crew waits 13 months for the next opportunity. 13 months they may not have. The return journey lasts another 3 years. Every system must continue functioning. Life support cannot fail. Navigation cannot drift. Communication cannot lose contact. Medical emergencies cannot exceed the crew's ability to address them. The crew that departed Jupiter must somehow maintain sufficient function to operate the spacecraft despite additional years of physiological decline. The equipment must somehow continue operating despite additional years of degradation. And finally, years after departure, the spacecraft must execute Earth orbit insertion and re-entry through an atmosphere that will destroy the vehicle if angles or velocities deviate from narrow tolerances. The thermal protection system has aged for nearly a decade. The guidance systems have accumulated radiation damage. The crew has been weakened by years of spaceflight. Everything must work perfectly one final time. The probability that everything works perfectly after 10 years of degradation approaches zero. Consider what informed consent means for a Jupiter crew. Astronauts accepting Apollo missions understood the risks. Equipment might fail. Calculations might contain errors. The moon was hostile and unforgiving, but mission planners estimated success probabilities above 90%. Astronauts accepted meaningful risk in exchange for meaningful odds of survival. The gamble was weighted in their favor. A Jupiter crew receives inverted odds. Success probability measured in single digits. Failure probability measured in certainty. They sign documents acknowledging that mathematics predicts their deaths. They train for years knowing that training improves their odds from hopeless to merely terrible. They say goodbye to families understanding that goodbye is probably permanent. This is not acceptable risk by any definition used in human spaceflight history. This is informed consent to probable death, dressed in mission patches and launch ceremonies. No astronaut selection board has ever approved such odds. No space agency has ever proposed them seriously. The math does not permit heroic exceptions. This is the mathematical consequence of reliability calculations applied to realistic system lifetimes and failure distributions. Components fail according to probability functions that grow increasingly unfavorable as time extends. Extended operations allow failures to accumulate until critical thresholds are crossed. A crew that attempts to return from Jupiter is betting their lives on a proposition that mathematics says they will lose. Getting to Jupiter was never the real challenge. The outbound journey tests human endurance and engineering capability severely. These tests have answers within the boundaries of physics. The solutions are expensive, difficult, and dangerous. But solutions exist. The return journey has no solution. Every approach that addresses one constraint worsens another in the interlocking web of requirements. Every technology that might help remains speculative, decades from development, or insufficient, even if fully realized. Every mission architecture that successfully delivers crews to Jupiter cannot return them to Earth. The crew that departs Earth on a Jupiter mission departs knowing they will not return. Not because of heroic sacrifice in service of exploration, not because of one-way colonization ambitions that trade return for permanent settlement, because the physics of the solar system do not permit round trips regardless of intent, preparation, or resources applied to the problem. Perhaps someday technological breakthroughs will change this calculation. Perhaps propulsion systems will emerge that transcend current limitations through principles not yet discovered. Perhaps medical advances will address the biological constraints through treatments that halt or reverse spaceflight deconditioning. Perhaps engineering reliability will improve beyond current understanding through manufacturing revolutions not yet imagined. But these hypothetical futures do not exist today. They may never exist. And planning missions around technologies that do not exist is not engineering. It is wishful thinking, dressed in technical vocabulary. The honest assessment is uncomfortable for a species that reached the moon within a decade of deciding to try. Human beings can travel to the moon and return. This has been demonstrated repeatedly with crews who lived to describe the experience. Human beings can probably travel to Mars and return. This will likely be demonstrated within coming decades if programs proceed as planned and challenges prove manageable. Human beings cannot travel to Jupiter and return. This limitation derives from physical constraints that current technology cannot address, and future technology shows no clear path to addressing. Jupiter will remain a destination for robots until fundamental breakthroughs occur that no one can currently predict, demonstrate, or promise. This is not failure of imagination. This is not surrender to difficulty. This is not pessimism masquerading as analysis. This is acceptance of reality. The universe is vast beyond human comprehension. Distances between worlds exceed what intuition evolved for African savannas can meaningfully grasp. Energies required for travel between planets surpass what biological organisms can survive, or technological systems can reliably provide across the timescales such journeys demand. These truths do not diminish human achievement. They contextualize it within a cosmos that was not designed for human convenience. We have sent our machines to Jupiter. Pioneer 10 and 11 blazed trails through the asteroid belt. Voyager 1 and 2 captured images that reshaped human understanding. Galileo orbited for years, dropping a probe into the atmosphere. Juno continues its work today. Each mission returned data that expanded human knowledge immensely. These are genuine triumphs of human ingenuity and determination. We cannot follow our machines in person. Not yet. Perhaps not ever. The return problem defines the boundary of human presence in the outer solar system. Until physics permits otherwise, that boundary remains.